Hello everyone. In this class I will discuss about the boundary conditions. Suppose this is one boundary separating the two mediums. Okay, then there is a electric field. This is E1. Suppose this is medium 1 and this is medium 2. And this is the tangential component which is parallel to the boundary, and this is the normal component. This is En1, and this wave is entering into the medium number 2. This is E2. This is E10 2, and this is En2, right? They are the normal components, right? So we define the boundary conditions here, and the conditions are the tangential components in both the mediums are equal for electric field. Okay, so this is first boundary condition. E101 is equal to E102, and mod of dn1 minus dn2, it is equal to rho s. If surface charge density is equal to 0, it means there are no surface charges present, right, on the boundary. Then we get dn1 is equal to dn2. Okay, okay, so these are the boundary conditions, right, which we use in the questions, right? Let me solve one question. 2 homogeneous isotropic dielectric meet on plane Z is equal to 0 for Z less than 0, epsilon R2 is equal to 3. A uniform electric field E1 is equal to 5AX minus 2AY plus 3AZ kilovolt per meter exist in medium 1, then calculate E2. For z less or equal than 0, also calculate, this is the A part in this question, and the B part is calculate angles that E1 and E2 make with the interface C is calculate energy densities in joule per meter cube. In both dielectric and calculate energy within the cube of side 2 meter, centered at 3, 4, minus 5. Okay, so this is the question, right? So here is the boundary which is given, and this is the suppose E1. So we'll make two components, one is tangential and another one is normal. This is E tan 1 and this is En1. And the tangential component we can check here. Boundary is given Z. So this component is tangential and this component is normal. So it is 5ax minus 2ay. This is the tangential component, and normal component is 3az. Okay, so this is how we resolve this component. But what is the boundary condition here? E tan 1, it is equal to E tan 2. Okay, so E tan 2, the tangential component in the second medium, it is equal to 5ax minus 2ay. and second is dn1 it is equal to dn2, which is epsilon 1 en1 it is equal to epsilon 2 en2. And en1 which is the normal component, and what is the normal component? It is given 3az. into en2. So what is epsilon r1 which is given? Hi Trilochan, how are you? Epsilon r1 is given in the question, which is okay. So epsilon r1 is given. Wait 1 minute. Let me check this. What is epsilon r1? It is given 4. So I'll put here value 4 into 3az. It is equal to epsilon r2. It is given 3 into en2. So we'll calculate en2 from here, and which is equal to 4az. So what is E2? E2 is E tan2 plus En2, right? It is 5ax minus 2ay. So we will put the value 5ax minus 2ay plus 4az. So this is our answer for E2, right? This is asked in the question. Okay, so this is a E2. Then we have to calculate angles that E1 and E2 make with the interface. So let me check this diagram once. This is the interface here. And this angle and this angle, right? This angle is angle with the normal, and this angle is angle with the interface. Similarly, suppose this is here E2. So this angle is theta 2 and this angle is alpha 2. Okay, so the value of tan theta 1 from here, it is mod of E tan 1 divided by mod of En1. So tan theta 1 it is what is E mod of E tan 1? Mod of E tan 1 it is under root of 5 square plus 2 square divided by 3. So we'll calculate the value of theta 1 from here. Theta 1 is the angle with the normal. It is 60.9 degree. So alpha 1, which is the angle with the interface, will just subtract this with 90 degree. So 90 minus 60.9, it is equal to 29.1 degree. This is alpha 1 here. Okay, so theta 1 and alpha 1. Similarly, we can calculate the value of theta 2 here. So tan theta 2 it is mod of E tan 2 by En2 mod of what is E tan 2? it is 5 square plus 2 square divided by 4, right? Because En2 is 4 here, that we calculated, it is 4, so we'll put here 4. So we'll get the value of theta 2 from here, right? We'll get the value of theta 2. Okay, so the value of theta 2, it is 53.4 degree. So value of alpha 2, it is 90 minus 53.4 degree. So the value of alpha 2, it is 36.6 degree. So this is how we can calculate the value of angles with the interface and angles with the normal. You check here, this is the angle with normal and this is the angle with interface. This is theta actually, right? One second. This is theta 2, right? This is the angle with the normal. This is the angle with the normal, and this is the angle with the interface. Hello, hi Rohit, how are you? Now in the third part, what we have to calculate? Calculate energy density in joule per meter cube in both the dielectrics. So we want to calculate energy densities. So energy density, the formula of energy density, it is 1/2 epsilon mod E square. Okay, that we discussed, right? So in the medium number 1, epsilon 1, it is epsilon naught. The value of epsilon naught, it is 10 to the power minus 9 by 36 pi into epsilon r1, which is equal to 4 into mod E1 square. What is mod E1 square? It is 5 square plus 2 square plus 3 square and its whole square. So we'll solve it, and hi Yogesh Pandey here. Hello, how are you? It is 672, right, microjoule per meter cube. Okay, the unit of energy density is joule per meter cube. It is always represented in joule per meter cube. WE2, right, in the medium number 2. So in the medium number 2, the energy density will be equal to 1/2 epsilon 2 mod E2 square. So it is 1/2 into 10 to the power minus 9 by 36 pi into epsilon. Epsilon is given here 3 into under root 5 square plus 2 square plus 4 square and its whole square, right? Okay, also 10 to the power 6 will come here because this is given in kilovolt per meter, right? So so we'll solve it. So this answer will be 597 microjoule per meter cube. Okay, now one more question is asked in this, right? And the question is, calculate the energy within the cube of side 2 meter, centered at 3, 4, minus 5. So this cube will lie in the medium number 2 because Z is negative, because Z is given negative. So suppose this is the plane, Z is equal to 0, separating. So where is the cube? So cube will lie in the medium number 2 here, right? That complete cube is lying in the medium number 2. Okay, complete cube is lying in medium number 2, right? Then we want to calculate energy within the cube. Okay, we want to calculate energy within the cube. So energy is equal to, we will solve energy density into volume, right? So this cube is in medium 2, so we'll use the formula in medium 2. So what is the formula in medium 2? It is 597 microjoule per meter cube. Into volume of the cube, it is 8, 2 cube. So this answer, when we'll solve, right? So this answer is 4.776 millijoule. Okay, so this is our first case, right? In our second case, we take dielectric conductor interface. Okay, so we take dielectric conductor interface. Here, suppose this is a plane separating the two mediums, and this medium is dielectric and second medium is conductor, and electric field is incidenting. This is E1. So in the conductor, electric field is 0 as well as flux density is also 0. In the conductor, electric field is 0 as well as flux density is 0. So according to the boundary condition, we know E tan 1 it is equal to E tan 2, but E tan 2 it is equal to 0. So we will get E tan 1 is also equal to 0. Okay, so we'll get here E tan 1 is equal to 0 and mod of dn1 minus dn2 it is equal to rho s, but dn2 is also equal to 0, so mod dn is equal to rho s. So this boundary condition we can obtain and based on which we can solve one question. Question is, reason y less than 0 consists of perfect conductor okay, and reason y greater than 0 is a dielectric medium of epsilon r is equal to 2. If surface charge density rho s is equal to 2 nanocoulomb per meter square on the conductor, calculate electric field intensity and flux density at point A 3 minus 2 and point B minus 4 1 5. So the first point has negative y. Here y is negative and here y is positive. So this point is inside the conductor and this point is in dielectric. So inside the conductor, electric field is 0 as well as flux density is 0 because this point is inside the conductor, because y is negative here and this point is in dielectric. So in the dielectric, mod of d it is equal to rho s. So mod of d it is equal to rho s, and rho s is the surface charge density. It is given 2 into 10 to the power minus 9. And when we observe the direction, so this direction is ay vector. So this is 2 into 10 to the power minus 9 ay coulomb per meter square. And we can also calculate the value of electric field here, and which is simply d by epsilon. Epsilon is 10 to the power minus 9 by 36 pi into epsilon r, and epsilon r is given, it is 2. So this will cancel, this will also cancel. So electric field answer it is 36 pi ay. Volt per meter. Okay, so this is our answer. Okay, so this is the basically this is the boundary separating the two mediums, and this is the E1 electric field, right, which can be resolved into two components, and that components are E10 and En1. And this is the electric field in medium number 2, which can also be resolved into the two components E10 and En2. So So boundary conditions are E10(1) is equal to E10(2) and mod of dN1 minus dN2 it is equal to rho s. If rho s is 0, then dN1 is equal to dN2. Based on which we solved this numerical, two homogeneous isotropic dielectric meet on plane Z is equal to 0. For Z less than 0, epsilon R2 is 3. A uniform electric field E1 5x minus 2ay plus 3az kilovolt per meter exists in medium 1. Calculate E2 for Z less or equal than 0. Calculate angles that E1 and E2 make with the interface. Calculate energy density in joule per meter cube in both dielectrics and calculate energy within the cube of side 2 meter centered at 3, 4, minus 5. So first we resolve tangential and normal components. The interface is here given, which is Z is equal to 0. So this is the interface. So the tangential components are here x and y, 5x minus 2ay, and normal component is here 3az. So what we discussed, E10(1) is equal to E10(2). So E10(1) and E10(2) both are equal, so E10(2) it is also equal to 5x minus 2ay. Okay. So another boundary condition is dN1 is equal to dN2. So epsilon 1 En1 it is equal to epsilon 2 En2. So it is epsilon naught into epsilon R1 into 3az. Epsilon naught into epsilon R2 into En2. Okay, so En2 from here it is 4az. So E2 which is E10(2) plus En2 we will solve. Then this answer is 5x minus 2ay plus 4az. This is our answer. This we calculated, and we are asked to find out the angles, right? Angle with the normal and angle with the interface. So this is the angle with normal and this is the angle with the interface. This is the normal, this is with the interface. So to calculate the angles, what we are doing, we are using this formula tan theta 1. Tan theta 1 is, it is mod of E10(1) by mod of En1. So we'll put here the tan theta 1, it is mod of E10(1), it is under root of 5 square plus 2 square by 3. So it is 60.9 degree. And when we calculate alpha 1, so alpha 1 is just the 90 degree minus this theta 1, because this total angle is 90 degree. So when we will subtract this 90 minus theta 1, so we will get alpha 1. Second, similarly, you have tan theta 2, it is mod of E10(2) by mod of En2. Tan theta 2, it is under root of 5 square plus 2 square by 4. So theta 2 we will observe here 53.4 degree. So alpha 2, it is 90 minus 53.4, which is equal to 36.6 degree. And another boundary condition, it is dN1 it is equal to dN2. Now we are asked to find out the energy density. Basically this is called as energy density. So energy density is 1 by 2 epsilon 1 mod of E1 square. It is 1 by 2 into 10 to the power minus 9 by 36 pi into E1 square. E1, this is epsilon r, it is 4. Under root of E1 square, it is under root of 5 square plus 2 square plus 3 square, and it's a whole square. So this will get cancelled, and after solving this answer is WE1, which is 672 microjoule per meter cube. Similarly, we will calculate WE2. It is in medium number 2. When we are asked to find out energy, so energy, it is equal to energy density into volume. Right? This is energy density. Energy is equal to energy density into, simply we will multiply with the volume, right? Because joule per meter cube is the unit of energy density into meter cube. So this will cancel. So the unit of energy will obtain here, right? Okay. So we are asked to find out the energy within the cube. Just check here. Calculate energy within the cube of side 2 meters, center at 3, 4, minus 5. Okay. So here Z is negative. Here Z is negative. So Z is negative. It means it is lying in the medium number 2. So this cube is lying in the medium number 2. So it's simply using this formula. Energy is equal to energy density into volume. So just multiply and we will get our answer. 4.776 millijoule, right? So this is our answer. Energy within the cube. Now we are observing a dielectric conductor interface. So this is the electric field which is incidenting in the conducting medium. This complete medium is a conductor. Okay. Conductor has electric field and flux density, both are 0. So we have this boundary condition E tan 1 is equal to E tan 2, but E tan 2 will be equal to 0 because there is conductor. So E tan 1 will also be equal to 0. Similarly, mod of dn1 minus dn2, it is equal to rho s. So dn2, it is equal to 0. So mod of dn, it is equal to rho s. Dn is the normal component of the flux density. This is the flux density. Now based on this, we are solving one numerical. Reason y less than 0 consists of perfect conductor, and reason y greater than 0 is a dielectric medium of epsilon r is equal to 2. If surface charge density rho s is equal to 2 nanocoulomb per meter square on the conductor, then calculate E and D at point A 3 minus 2 2 and point B minus 4 1 5. So here at this point y is negative. So y is negative. So this is in conductor, and here y is positive. So this is in dielectric. In the conductor, electric field and flux density both are 0. So this is our first answer. This is our answer. Okay. And in the dielectric, mod of D, it is equal to rho s. So mod of D, it is equal to 2 into 10 to the power minus 9. Right. Rho s is given 2 nanocoulomb per meter square. So 2 into 10 to the power minus 9 A by coulomb per meter square. So electric field intensity, it is D by epsilon. It is 2 into 10 to the power minus 9 by epsilon is 10 to the power minus 9 by 36 pi into epsilon r is given 2. So electric field is given. Electric field answer is 36 pi A by. So this is our required answer. So this is how we solve the problems of boundary condition, electric boundary conditions. So thanks. We'll take the new topic in the next session, right? Okay, good night. Thank you very much.